right, hello everybody. I hope you're having a great day at Real-Time Analytics Summit. I'm Hyun Choi. I'm a software engineer and the tech lead of Pinot at Moloco, working at its data infra team. Before I go into my slides here, I know we're at the Real-Time Analytics Summit, but I'm actually going to talk about batch data analytics, which admittedly isn't as attractive as real-time analytics. But we see a lot of companies that start from batch and eventually getting to real-time. That's kind of our thinking as well. We want to get to real-time, but we have to start incrementally building from batch into real-time. So yeah, I hope that resonates with you a lot. I'll be talking about some of the things that we experienced while using Pinot and trying to get Pinot onboarded onto a lot of use cases. So before I get into all the Pinot, the technical stuff, I'm going to talk a little bit about Moloco. This is a quick intro to Moloco as a company. We're a machine learning company at heart. Our founders developed the ML engine behind YouTube and had a vision to democratize the power of ML for all businesses. And our operational ML platform was built on that vision. It's creating tremendous growth for advertisers. From a technical standpoint, more specifically on what we do, we are an ML company, as I just said. We specialize in Adtech, and our mission is to empower businesses of all sizes to grow through operational machine learning. So that's all good. So we're doing Adtech, we're doing machine learning. So what does that kind of mean in terms of the data, the analytics, the workloads that we do? So with Adtech, some of you might have experience with Adtech, but the thing is, the scale of data that Adtech companies have to process is massive. And there's an incredibly high cardinality data. We have like 70, 80 dimensions in some cases, and that tends to explode in size of data. We have petabytes of data, a lot more of that actually stored in our data. We have to run analytics workloads against that data. So to kind of like to give you the setting or context behind why analytics is important for us, doing good analytics is pretty hard. And we had to find like the really good technology to support our use cases in that regard. So in terms of numbers, these are some of the numbers that we like to use a lot when we advertise like what, the scale of data that Moloco processes. So we process about 10 petabytes of data each day into our system. And at peak processing, we are receiving more than 6 million queries per second. So now all of this data, not all of this data will be used in the actual end user end analytics, but some of them is summarized, but still even at the end, because of the raw size of the data, initially, there's a lot of data that ends up in so dashboards and such. So that is all about Moloco. I'm probably not going to talk too much about my company at this point. So what's this talk about? So I'm going to talk about Pinot. Obviously, and how Pinot helped solve Moloco's long-time challenge of slow dashboard latency. More specifically, I'm going to talk about how we adopted Pinot as part of our data infrastructure, the data analytics challenges we are facing, the use cases we wanted to target, and the requirements. And also we'll go into some of the things we built in-house that worked well for us in rolling out Pinot. So before I get into the Pinot part, I want to give you an idea, just a really rough, simple idea of how data analytics works at Moloco. First off, we are primarily a GCP company. So we're very heavily using technologies such as BigQuery or GCS or Bigtable, all that sort, which are great tools. And using these tools, we mainly have, say, like 3 worlds of data. There's the world of raw logs, and where microservices are writing logs in a streaming manner or in a buffered log writing manner to BigQuery or GCS. This is all that 10 petabytes of data coming into our system. And after the raw logs come in, we process them using either BigQuery or Dataflow, and these end up as source of truth tables. And after creating these source of truth tables, again, these source of truth tables are post-processed using BigQuery or Dataflow again to become analytics tables. And these analytic tables are the things like fact tables or dimension tables that you might have seen in data analytics patterns while working at your own companies as well. So yeah, these analytics tables at the end are queried by different sources. We have some in-house data visualization tools. We have Looker. We have things like Superset that are running. But anyways, there are a lot of end products that users are using to query the analytics tables created at the end here. And to kind of like get to a really simple statement of what our problem was. So at the last part of the diagram, you might have seen some analytics tables at the end. These analytics tables, well, dashboards querying these analytics tables were just taking a lot of time. And by a lot of time, these queries would sometimes take up to 10 minutes to run. And sometimes that's okay, and sometimes maybe it could take hours, and we could still be okay with it. But the thing is, we had a lot of use cases where people, Molocans, data scientists, engineers, they would come into the system, they would look at this dashboard maybe 100 times a day. And if you think about that 10 minutes every 100 times, that's a couple of hours, or a lot more than that, almost a day, actually, in some cases, right? So that was putting a toll on our productivity in terms of data analytics. So, right, so 10 minutes, that's really slow, and these queries are taking a long time. And you may ask the question, like, why is it so slow? So the answer to that is our data is really big, and running aggregation and analytics queries against some of these big data sets can just be really, really slow. And I'll probably get into more of why this is so slow and why there are certain requirements that we have to keep that make these queries run really slow. So now we've talked a little bit about the rough problem we were facing. I'm going to talk a little bit more about the specific use cases we wanted to support at Moloco. This is not all of the use cases, but this is more a little bit of a simplified version of the use cases we are facing and some of the key cases here. So one of the biggest use cases we wanted to solve was our internal performance analytics portal. And it's safe to say that this portal is very important to us because it answers questions such as how much revenue is being generated right now, and how many clicks are being generated per campaign, and how many installs are we getting out of, say, each country. And these are easy to say sentences, but you can easily imagine how this can turn into a lot of weird queries, like how many installs are you getting out of campaign, country, operating system, iPhone version, such and such, right? So this is really important. So one of the things that Moloco did was invest a lot of our time into building our in-house tool for performance analytics. That is the use case we wanted to help out with. And because this is such an important thing, and they had to care about user experience a lot, they were initially suffering a lot of high latency problems. And to solve that, they actually did something really crazy, was build their in-house query processing framework over Bigtable, which is really crazy because not a lot of people actually do that. They'd probably look for a new query engine, right? But anyways, that was all working well. But in the end, it started kind of blowing up because we were getting some good performances, but if we wanted to add more dimensions, more cardinality into the data, we were seeing that this Bigtable abstraction was not helping us too much. So anyways, this was really just not meeting the requirements in terms of, say, dimension cardinality or query latency. So kind of like getting a glimpse of the problems we were facing. And let's expand on this use case a little more. So you can think of these use cases as like derivatives of the good old SQL statement we probably have run once in our career. So you take a date and you sum a spending or a metric, and you group by that date and order by that date to see how much has spending changed over the course of time. So what are the challenges with this kind of query pattern that we were facing in the case of the performance analytics portal? So first, the cardinality was still really, really large in these performance tables. There were sometimes up to 40 to 50 dimension columns for some tables, and that might not sound a lot, but adding one dimension incrementally adds a lot of complexity, a lot of explosion in terms of data size and query latency. Imagine having, say, 3 or 4 enum values for a dimension. Actually, we have like 100,000, we have dimension columns that have like 100,000 or a million cardinality, which is horrible already. But anyways, if you add more dimensions, you see basically storage exploding by 3 times and also kind of query latency almost exploding by 3 times as well. So the cardinality is a huge problem, but one of the problems was that, you know how it is, like, you know, when you're working with a team, they want a lot, and this team wanted both lightning fast analytics. So for certain set use cases, they wanted dashboards to render in a lightning fast speed in, say, like 100 milliseconds, 200 milliseconds. And they also wanted flexible data exploration as well. So you know how it is. I'll explain a lot more about like this flexibility part, but it's really difficult to do lightning fast analytics and flexible data exploration at the same time, right? And another challenge is joining with dimension tables. And that also adds to, say, like eroding the query latency, because, you know, reading data, aggregating data by a set number of dimension columns, that's pretty okay to do. But once you start adding the complexity by joining with dimension tables, and now I'll explain why we have to do dimension tables in the first place, but this adds a lot to the query latency just due to the nature of the computational nature of joins. And the last challenger, good to have, was a lot of the data is already in-house in our cloud, our GCP projects. So kind of good to have is, can you just seamlessly integrate Pinot with our cloud for efficiency in terms of, you know, human resources and such. The next use case I want to talk about is kind of similar, but slightly different in nuance. So we have another internal use case where I'll just call it the A/B testing platform within Moloco. So one of the things we did was we built our in-house A/B testing platform. What do we use it for? We do it to, say, launch a new feature, launch a new type of bidding, or, you know, a lot of these Adtech knobs are being turned on and off at all times. Maybe it's a different value we want to try out, or threshold. Every time we want to do that, we want to be data-driven. We want to understand what that, how that influences our system in terms of, like, say, revenue, in terms of such different metrics. It's actually a lot more complicated than that, but I actually don't know too much about it. But we need to be really data-driven. We need to be really careful about how metrics change whenever we make changes, right? So what this team, as similar to the performance analytics team, was doing a lot of these experiment level queries. If we have two groups, if you compare them, how have the metrics changed? How has ROAS changed? How has Moloco ad spend changed? And these queries are actually the ones that are taking up to 10 minutes to run. I'll get a little more detailed on that. So yeah, even with this case, not a lot is shown in the diagram over there, but there are a lot of metrics and a lot of dimensions that this platform has to support in terms of, and that's a lot of data analytics, query latency, bottleneck being added there. So let's look at the challenges here as well. You might notice that this is very, very similar to the first use case. The cardinality is slightly smaller in this case. This can grow up to maybe 30 dimension columns, but which is much, much better, but it's still very high cardinality. Even in this case, users really want just both lightning fast analytics and flexible data exploration. You know, you never know what data scientists might want to check out. They say, oh, I want to go really slice and dice really deeply into a certain set of dimensions and see from there. So you need to do both flexible, but in the base use case of, say, I want to just check the results per campaign. For those simple cases, they have to be still really, really fast. And a different thing, slightly different thing from the first use case of performance analytics portal was that the joins were becoming a lot more difficult. For the first case, a lot of the queries were simply written by just one join between a fact table and a dimension table. But with this case, there were 7-layered joins. You know, we would join with a fact table with another table. We would join between dimension tables and then join again with fact and dimension tables. So the complexity of joins was significantly larger than the first use case. So that's something to focus on. But yeah, and other than that, you know, the similar integration challenges. You know, people don't want to change too many things when, you know, changing technology. So we wanted a lot of these new tables to be seamlessly integrated with our infrastructure. So let's do a quick recap of the requirements derived from the challenges we were facing with these use cases. So first, it'll be great to be able to get both performance and flexibility at the same time, which you may know is not always easy. And it'll be great to be able to do fast joins with dimension tables, maybe multi-joins and nested joins, such and such, for both use cases. And finally, as a bonus, easy, low-effort integration with existing infrastructure would be great as well. So, so I'll look into these each bullet point, and explain how StarTree Pinot helped us meet those requirements. So first, performance and flexibility. It's no myth that in most cases there's a trade-off between performance and flexibility, right? On one extreme end, if you want to get just best performance, the best performance for your use cases, I know this is a little extreme, nobody would really do this, but you might just think of pre-computing and creating tables for the results for all of your use cases, right? Like if you have one query pattern that is derived from one source table, another query pattern from another source table, you can create two pipelines that create sort of like a materialized view of this table into separate tables. And in that case, because since everything is pre-computed, you will get great performance. But the downside of this is that you would no longer be able to just use one table to serve your queries, right? So there's some flexibility, and there's a lot of confusion and there being multiple tables to look at for your use cases. And on the other extreme end, I just covered the best performance case, but for the best flexibility case, what you could do is just fit everything into one massive table, right? This would contain all the raw logs, all the dimensions, all the metrics, so you don't really need to think about how many tables there are. You could just create one table and run queries against a subset of dimensions and metrics of this table. So that's great. So, and obviously, you would get a lot worse performance across the board for all of the pre-existing query use cases because you just added all of them up. You just added all of the cardinality, all of the metrics into one table. So that's pretty big explosion in terms of the computational complexity here. So what is our solution? We discovered this thing called StarTree indexes. I'm sure there's a lot of people here in the room here that introduced us to this concept. And to our surprise, this is a really great abstraction. So kind of like to give you an explanation of what this is. So these are Pinot indexes that we kind of think as abstractions or just indexes for aggregations. And to use this, you decide the dimension columns and metrics columns. And when you run aggregation queries with any subset of dimension columns and metrics columns, you get excellent query performance because the results of this aggregation, the sub-aggregations, have already been stored in the StarTree index here. And the really good thing is you can attach multiple StarTree indexes to a table. So if you have multiple different query patterns that kind of overlap, but they're somewhat different, you can add them and you can support all the use cases that fit within each StarTree index. So to solve the problem of gaining both performance and flexibility, one of the things we did was we didn't go in that route of creating a table for every use case. What we did was we created a big table with all of the dimensions and metrics columns. And we decided which query patterns we wanted to optimize for this large table. And for that individual query pattern, we would create a corresponding StarTree index. And because of that, we saw performance really, really fast for the optimized use cases, right? And one of the questions that you might also think is, doesn't that limit performance optimization for only a small subset of query patterns, right? Because theoretically, you can't create a StarTree index that contains all the dimension columns and metrics columns, and that's supposed to be an anti-pattern in itself. But what we realized is that in practice, most visualization results that are meaningful to users. So normally we wouldn't have millions of rows coming out of StarTree indexes to a dashboard because human beings aren't really able to recognize that amount of data in a glance, right? So if you're essentially doing meaningful data analysis and visualization, the number of rows, the number of cardinality of rows coming out of your query results are pretty small. And because that query result is pretty small, StarTree indexes are technically able to house that sort of house that number of rows pretty well. So let's look at another requirement, fast joins with dimension tables. Just in case some people may not be familiar with what fact tables are, what dimension tables are, I'll try to give a brief explanation via example. So imagine the case where we're tracking spending per date and advertiser. So in a fact table, and if you're doing this with a fact table, you won't really store auxiliary information such as advertiser, the name of the advertiser, the country where the advertiser is in, and such things. But you would store the core details such as so the time column or the date, the advertiser ID, and say the spending metric for. But you can think about adding more metrics naturally to the set here. And how would we get things like advertiser name or like the advertiser country? So in this case, what we do is we add something called dimension tables. And in adding a dimension table, we would store both the advertiser ID and the advertiser name or any other sort of key value-ish data into that dimension table. So whenever we want to get, say, the amount of spending per advertiser name or per advertiser country, we would left join the fact table with another dimension table, and that using the key of advertiser ID, and that would be sort of like a very established pattern in terms of data analytics. And one of the things we get asked a lot is, can we all pre-join the data? Because we've had conversations like, can't we just, because a query pattern, if you have, say, a fact table and a dimension table, you have all of that data beforehand. Can we just join all those together, form a pretty big table, and store that in BigQuery or Pinot and query against that? So this doesn't really work. I wouldn't say this doesn't always work, but it didn't work for us because for our case, we noticed that the auxiliary values, so like the name of an advertiser or the country of an advertiser, these values tend to change very often. So if we want to keep everything pre-joined and also want the data to be correct whenever these values change, we would have to backfill every time the dimension value changes. Well, maybe not every time, but how we would have to eventually make it consistent by backfilling for the dimension values that change across our historical data sets, right? So, and back to the topic of like how Adtech has big scale and cardinality, maybe if we didn't have that much cardinality, it would be feasible to run those backfills every time a dimension value changed. Maybe that's possible, so you can maybe do a whole refresh of the table. But in terms of computational cost and efficiency, backfilling a table, single table, with our scale might cost $400,000, $500,000. So it wasn't really feasible to do that all the time, right? So our conclusion was that the cost of backfills, the maintenance cost that that comes out of pre-joining everything wasn't really in our picture here. So doing that will far exceed the benefits of whatever we do. So yeah, well, that is the whole thing about dimension tables and joins. So where we are at now is we have to figure out how to do fast joins with dimension tables between fact tables and such, right? So surprise again, we actually found out that StarTree indexes were extremely helpful in getting this done. So when it comes to joins and shuffles, you may know that reducing the cardinality of data being joined is immensely helpful. So in our case, this would be the amount of rows in the fact table, or the amount of rows in a dimension table being joined together. If the number of rows being joined are large, the complexity increases, and the query performance naturally degrades into something like seconds or minutes. So how does that connect with the StarTree index here, right? So I'll actually cover a query example here. So on the left, you have a join between a dimension table and a fact table, where the fact table is denoted as F and the dimension table is denoted as D. So if we try to, so one of the ways of writing that query of like left joining, grouping by, is to list all of the dimension metrics over there, we can left join first, and we could do a group by later based on all the dimension columns that were derived. The issue with this is that let's imagine that if we have a fact table that has a StarTree index configured for the dimension metrics here, we wouldn't be able to utilize that StarTree index, right? So we noticed that Pinot wouldn't pick up that index information. It would do a naive left join and group by in a naive manner. So that led to a lot of bad performance. So what we did was we sort of optimized most of our query patterns. So this is a really simple simplification of the optimization we did here, but we did a lot of this for a lot of our joins. So we split the join between, say, first, we would group by the fact table information first, and by doing that, because now we're having a subquery pattern that is able to utilize the StarTree index, the first part of the aggregation happens really, really fast. And because the cardinality was decreased by performing the group by, later left joining with the dimension table also happened a lot faster. So initially, when we were doing, say, running naive queries against the A/B testing platforms queries, we were seeing query latencies of a minute, 3 minutes, 5 minutes. And after getting this optimized, all the patterns, by using all the StarTree indexes, we saw query patterns be optimized to about 500 milliseconds to 2 seconds, or around that range, right? Which is much faster than the minutes we were seeing initially, right? Okay, so we covered the joins with dimension tables and how that could be done with query optimization of StarTree indexes. For our final requirement, I'll cover a little bit about ingestion. I had mentioned that as part of our requirement, it would be great to do easy to use, seamless integration with our infrastructure. So one of the requirements, I was pretty serious about the fact table stuff and how dimension table stuff happens. And from that, you would imagine that we would have to do sort of like a first-class ingestion of time series data or fact table into our system. We would also need to do a pretty seamless integration with our dimension tables. So we would need to get that into Pinot ingested every now and then pretty reliably. And also idempotence. This is a term that comes up a lot in data engineering. So essentially, we might want to run ingestion jobs, the exact same ingestion jobs a multiple number of times. If done badly, data might be duplicated because you maybe inserted the same range of rows for a time interval twice, and you'll get duplicate, right? So it'd be great to not have that sort of characteristic and guard it with idempotent data ingestion. So first part, time series ingestion, how do we get that solved? So if you look at StarTree Pinot, there's an ingestion library called SQL connector batch push task. That's kind of a long name. But essentially what it does is it's able to read from SQL data sources such as Snowflake or BigQuery. So you can check out the docs here on exactly how to use that. But if you use that, you're able to, you can provide a query pattern to, say, the Pinot's ingestion library, and it would run that query against BigQuery or Snowflake. For our case, it is BigQuery. And ingest, get that query results, the rows, and update the Pinot table, the destination Pinot table for that given data interval. And what was really, really good for us was we noticed that if we provide a data interval for that ingestion task, idempotence would just happen out of the box, right? So we don't really have to worry about, hey, did we get multiple segments that are duplicate into our system? No, because we provided a data interval, the ingestion would just kind of flush out the existing segments in that data interval and add new segments in there. And that was an incredible abstraction for us when moving forward, because you wouldn't have to worry about that part of the complexity, which is a huge problem. So what we did, there's a multiple number of ways to use SQL connector batch push task, but we could use it by creating an ingestion task with Pinot's internal scheduler. We could invoke it using API. What we did was we invoked it using API from the Airflow part, a pretty heavy Airflow company. So we created an abstraction over the API call to SQL connector batch push task. And we had users provide arguments such as data interval, query time bucket. Once that is provided, we connected that with Pinot's API specification, and it just kicked the ingestion on the Pinot side. We would subscribe to the changes or the ingestion results that happened on Pinot. And for the dimension table ingestion, it was very similar to time series. There's something called file ingestion task, which essentially is sort of like reading results from a file, getting the rows, and kind of get that synced with a Pinot table. So we had a Pinot table that was essentially a dimension table, and what we did was we abstracted over a file ingestion task. We had users provide things such as query, table name, or things such as schedule, the cadence of how often you don't want the update to happen. And if you do that, so we had, what we would do is, in our ingestion library, we would get that query content, we would get that table name, we would copy that over to GCS in Parquet format, and the file ingestion task would crawl from that GCS bucket, or the Parquet files, and sync that with the segments in Pinot. And last, finally, one thing I want to mention is the Pinot CLI. This was actually created by our intern back then, who was actually sitting, I think, right over there, which is an amazing thing to witness. So what this tool does is, with the CLI, you can create, delete, update Pinot tables, run ad hoc backfills, et cetera. There's a lot of features. You could check ingestion results. This really helped us create more tables and pipelines on Pinot a lot efficiently, and this was extremely crucial as we landed more use cases. For the first 2 use cases, this is marginally helpful, but as we got 5 to 10 more use cases landed into Pinot, without this tool, we would have been spending a lot of time, clicking buttons on the web and not being able to automate any of our use cases, right? So yeah, we are right now. So initially, we had this toolkit with creating table, delete table, up table, but right now we're in the process of developing this even more so that this is just generally accessible for all Pinot users within Moloco. So if you're thinking about using Pinot, I actually recommend investing in tooling like this. It's going to make your lives a lot easier. So how did Pinot change our data analytics architecture? Actually, not much. And I mean that in a really good way, because we're a relatively small company, and we need to move in an agile manner and able to be productive. We can't just declare, hey, we're going to go real time, and ask everyone to go real time. Hey, can you get your data into Kafka? It really doesn't work like that, right? You want to make incremental changes. You want to see impact being landed every month, every quarter as you go. So yeah, not a lot of changes, but if you look at the diagram here, you remember that there were initially the raw logs, the source of truth tables, the analytics tables. What really just happened was we took a lot of the StarTree indexes, all the ingestion libraries of Pinot. We added an optional last step in our data analysis infrastructure where you could take the existing BigQuery data into Pinot, and we would have our in-house use cases querying the Pinot database over here. So I'm almost about to wrap up my talk here, the TLDR and the takeaways. So we adopted StarTree Pinot. It is really, really huge, largely successful. We have about up to 100 tables now at our cluster, a total of 50 to 100 terabytes total. And just want to kind of emphasize, we only started with 2 people initially, me and our intern over there. But it started with 2 people. This adoption happened over a couple of months, and it has been wildly successful. A lot of people want to use Pinot within Moloco recently. So just want to point that out. And for us, keeping things simple and incremental helped immensely in landing impact. So we didn't completely overhaul our architecture. We thought of Pinot as a very natural extension of our existing data infrastructure and optimized use cases we could from that extension. All right, last, I just want to give some shout outs, kudos to people here. Our data infra team at Moloco, Andrea, Marina, Rob, who's worked with us on Pinot, getting the use case landed. sending my gratitude. And on the StarTree team, Will, Manesh, Ryan, Sandeep, who's helped with onboarding and getting the use cases evaluated initially. So yeah, thinking a lot of gratitude for that as well.
For your A/B testing, did you, you're using pure count distinct or some sort of like HLL, and did you get any pushback on like being off by 1 or 2% for like a randomized control trial, basically?
Oh, so because we have 100% exact data, the accurate data in BigQuery, we said, if you're naturally extending Pinot as like extension of BigQuery, we get the data, the exact accurate data from BigQuery to Pinot. So the HLL aggregation, the approximations aren't really happening at the moment. So no issue on that part.
So you mentioned, so this is great for improving query latency. Are you looking to improve the freshness, and maybe not in the short term? You mentioned it's not as simple as putting stuff in Kafka, but how would you imagine evolving this to also do everything in sort of real-time ingestion latency?
So we're thinking of it as a really long-term project because in order to do real-time, to do real-time, you have to get everything real-time, right? From the ingestion, the initial ingestion, to the processing, to the end database. So for this case, Pinot is the end database, and you can do real-time with that. The challenges we're facing is that, say, like if you want to do 6 million QPS data ingested into something like Kafka or something like a PubSub or messaging queue, that amount of data is a lot of millions. I'm not sure if that's actually more than 10 millions or something like that, and that's a lot of money for us. So we want to be really careful about which things we want to do in real time or not. And it's very interesting for us because a lot of our use cases, some of them benefit from being in real time, but some of them are actually very latency agnostic because for a lot of the data that comes in and for the metrics to be finalized, there has to be some amount of delay. Like we have a lot of external vendors that are sending us data, and if they're not sending us the data in real time, we can't really do at full real time, right? So, so kind of a long-winded way of saying that we probably can't do everything real time, but we're thinking about like certain use cases. Hey, this is cost effective. This is also this creates value for the use cases and our client teams at Moloco. So that's my rough take on it.
So you talk about such a big data and those many queries. So how big your Pinot cluster is?
Right now, I think we have about 24 servers, and those servers I think those servers are the 16 high mem machines, 16 vCPU high mem machines. I think we have a total capacity about 100 terabytes or not. That's probably the numbers I'm seeing right now, yeah.
Thank you for the presentation. I really liked how you presented the optimization for the dimension and facts. I'm wondering if you're allowing like data scientists to perform ad hoc queries, how are you monitoring for like slow performing queries and making sure they're using these like sometimes manual optimizations and making sure they're not, affecting the performance of the cluster?
So right now, and kind of like going against the question here, but we're not really using Pinot for ad hoc data science queries. We're using it for a lot of business intelligence queries and data exploration there. Honestly, and on that end, we had a couple of issues where people would add all of the dimensions to a Pinot table and against the Pinot table, and they would query for the last 2 to 3 years of data, and that would explode the server sometimes. It was pretty sad to see that happen. Right now, we don't have a strong safeguard, so one of the things we did with our customer teams is like, hey, let's be realistic. We can't really support that data. People don't really need it as much because it's being visualized into a dashboard system, right? So we have front-end, client-side blockers to stop that from happening.